Hello, my name is Orfeo Bertolami. I work at University of Porto in Portugal, and I'm going to discuss a physical framework for the Earth system and show how it can be used to gauge the human impact. This is work done mainly in collaboration with Frederico Francisco, and I will describe what has been written in these papers listed at the bottom of the page. Of course, you want to understand how this Earth system evolves. As we know, since 1950s or so, the system is being dominated by human intervention. We live at the Anthropocene. And this, of course, hosts an incredible amount of complicated problems. Among them, climate change and the sharp rise in the average temperature of the planet, whose predictions show that will be catastrophic by the end of this century. In order to see how the system evolves, of course, we need its evolution equation. It comes with the name of the Anthropocene equation. And in fact, it was the very object of our paper that appeared in Global and Planetary Change in 2018. The idea was to describe the various transformations of the Earth system, very much like phase transitions in physics. As we know, this can be done through a very general formalism, of Landau and Ginsburg, on which these transformations, these thermodynamic transformations, are understood in terms of variations of free energy and are given in terms of order parameter psi. As well as dynamical variables, which in the case of the Earth system are internal dynamics, thermodynamic ones, are astronomical ones or geophysical ones, but also lately are dominated by human activities. If you know how to build this free energy, you can, of course, get its time derivative. And this is the case in which the system is dominated by human forces. Will give you the Anthropocene equation, the very first equation that appears at the bottom of this page. Of course, this allows you to understand also the great acceleration of the human activities in the very same terms. The order parameter is chosen to be the average temperature with respect to the Holocene temperature, on a very stable phase in the history of the Earth system. This free energy now can be built according to the formalism in terms of a polynomial of this order parameter and its derivatives, with coefficients which can be built in terms of the analytical expansion of these dynamical parameters. A simple description of the system would be therefore this free energy in terms of a simple polynomial, and you can see that it immediately leads to two different types of minima, one on which the minimum is at 0 and one on which is different from 0, corresponding to the situation, the first one to the Holocene clearly, as the equilibrium temperature is the very one of the Holocene, while the two other equilibrium states correspond to a greater and a lower temperature. The human activity is modeled here the very way, for instance, a magnetic field is introduced in the Landau-Ginsburg formula through a linear term in terms of the order parameter, and this term clearly leads to a new equilibrium state, as shown in this picture here. A new equilibrium state in between that leads the system to evolve from the Holocene towards this new equilibrium, and this transition is what we call the Anthropocene. In order to see how this transition takes place, we have considered the system in terms of its phase description, and this has been done in this paper that appeared last year. And this was achieved through the Hamiltonian formalism, which can be straightforwardly obtained from a Lagrangian. Lagrangian has a kinetic term, which involves at the Anthropocene the term of the velocity of the temperature and the potential, which is the very free energy. the Hamiltonian system can be therefore immediately obtained. This is standard, and from the Hamiltonian you can get the equations of motion. Graphically, these equations are in the absence of human intervention, are orbits around the equilibrium of the Holocene. However, as age grows, you see that these orbits get distorted and the equilibrium point shifts towards a situation in which the psi is greater, which means that the temperature of equilibrium is greater than the one of the Holocene. In order to be a bit more realistic, you have to introduce dissipation. This is done through standard methods by a term proportional to the velocity of the temperature. And assuming that human action is proportional to time, which is a very conservative statement, we can see how the system evolves. Clearly, it will do so from the Holocene towards a deeper state in this three-dimensional diagram, which is in this third dimension, where the equilibrium situation corresponds to the bottom of this graph, and which the equilibrium temperature is greater than the one of the Holocene. This, in fact, is very much what has been predicted with Stefan and collaborated this very influential paper that appeared in PNAS in 2018, in which they predict that your system, which in fact evolved very much like we have shown in the previous slide, from the Holocene towards a state in which this equilibrium temperature was greater. That's hothouse scenario. Next is the issue of how to quantify these human activities. The idea is to use the well-known planetary boundaries, these 9 variables that describe the state of the system, and consider them with respect to the so-called safe operating space, their values at the time, at the period of the Holocene. And therefore, we viewed age in terms of these planetary boundaries, and we go further, introduce interaction terms between them, between 2 of them, 3 of them, and so on, and see how they impact on the evolution of the system. This was done in this paper that appeared at the Anthropocene review earlier this year. I do not have time to describe, but this leads very naturally to an accounting system with the system of quotas, as described in this point 4 here. And this can be also shown to work on a situation on which you understand very well the impact of 2 different planetary boundaries on each other. And in order to exemplify that in our paper, we have considered climate change, let's say carbon dioxide concentration, and its impact on the ocean acidity. This is done through well-known chemical reactions involved in the CO2 in the atmosphere being dissolved in salty water. This leads to carbonate acid. The kinetic of these reactions are shown here. These concentrations are initially known, and through a linear interpolation, as depicted here in point 3, we can get their values from the data. This is how it's done. I'm afraid we will not have much time to describe it, but this linear interpolation lead us to this calling of year 2020, and in particular, these red values are the ones that we predict. And you can see that, for instance, what concerns carbon dioxide, our prediction is very much on the mark. So in order to see the impact of that, we can compare, for instance, the values of H1 and H2 with interaction term. And you see that with respect to H1, for instance, the interaction term is an order of magnitude smaller, meaning that the interaction term is of order of 10% or so it's small, but it's not negligible. And therefore, if you consider, for instance, the scale of an year, any quota that we establish won't be shifted by this interaction to more than, let's say, 10% or so. Let me close down with a word about the management of the system. This is a complex issue, but the idea here is to propose digital contracts using the techniques of blockchain, and the system would operate in the following way: a local node of this system of nodes who initially decide to subscribe this digital contract voluntarily. They aim to restore local ecosystems, and one of these nodes decide to do so, and they submit this work to follow the other nodes, and the proof of work of the other nodes is to verify that this ecosystem has been properly restored. And once this is consensually agreed, the local node that performed the work gets some payment in the form of a new crypto coin that we call the PB coin. So the idea is that this initially works on a voluntary basis, and as the system evolves, it becomes scaled up so that it may have an impact on the Earth system as a whole and on its evolution. Thank you.